All right, so in this video, we're going to continue studying the concept of the derivative, and we're going to look at, the formal equation. So here it is. We read this as the derivative of f at, some point x. Sometimes we, like in the previous lesson, we wrote c, same thing. X is just a value for c, or c is a value for x. Now we read this as f prime of x. It's going to be very common for writing or representing the derivative of a function. And so the f prime of x is equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x, provided that the limit exists. And we're going to get into like where it cannot exist and the concept behind that. So we're going to also then do some practice, going through a limit process using this formal equation. But first, let's understand graphically what the limit, what the limit represents when we're using it to represent the derivative. Oh yeah, also before I jump ahead, it's important that you understand that f prime, or the derivative, is also a function. So the function of a function. I think it's very important to make sure that you wrap your head around that and don't let it confuse you, because it's going to be, big, the big deal down the road in the next couple of chapters. All right, so let's understand, what's going on when we're talking about the graph of the derivative when compared to the original function. So here, we're given the graph of the function, and we're going to then sketch what we think that the graph of the derivative would look like. So let's, first label this x, y. Now, let's also make sure that we don't confuse the scale, because the scales aren't exactly the same, but roughly. So we could say this is at 1, 1, and we'll say maybe this is at, like 2, 3, 4, 5, that sort of thing, just to make sure we're on the same page as that. Now, let's again recall that the derivative of a function describes how the function is changing, and it can be approximated geometrically, as the slope of a tangent line at that point. So let's say, for example, we want to understand the rate of change over here at this point. A tangent line will maybe be something like that. Now let's look at what about over here at 1, when x is 1. A tangent line would be something like this. And let's look at when x is 2. A tangent line would, on the graph be something like this. And then when x is 3, the tangent line would be, maybe kind of somewhat horizontal, we could say, could argue. At 4, whoops, that'd be something like that. And at 5, my tangent line would be like over there. Okay, so now let's make sure we get this next part down, because this can be something that confuses students a lot at first. Now, when x is 0, the slope of this tangent line, we can maybe say it's like, -2. So we'll say f prime, we'll just say -2. Now, so when we're going to graph that on here, we would, probably need to drop this. That being said, -1, -2. The y coordinate will be the derivative. It's going to be essentially what's representing the value of the derivative. So we can say y is equal to f prime, or we can say f prime of x. X is still x. So at this, to represent this derivative, f prime equals -2, we're going to graph it, you know, still along the line x equals 0, and we're just going to put a point there, just a point. That's it. Now, over here, you know, I would probably say that this is roughly, you know, equal to 1. So when x is 1 over here, y is 1. So then we just plot a point over here at 1, 1. That'll be the next point. You're still going through this slowly. Now we look over here when x is 2. When x is 2, you maybe say that this looks pretty steep. This looks like maybe that the derivative is -3 here. We'll say that the derivative is -3 when x is 2. So when x is 2, we're going to put a point down here. So we can, let me just note it as 2, -3 to represent this right here. Now when x is 3, this is going to be kind of a simple one. The derivative is just a horizontal line. So the derivative is just going to be equal to 0. So that horizontal line is 0. So at 3, we just plot a point over here. I'm going to go ahead and label these so we are clear about what the values are. That's 4 and that's 5. All right, now at 4, we're getting, you know, back in the positive direction. This is probably 1 again, I would say. So f prime is, you know, roughly 1. And remember, this is an approximation to get the, you know, our conceptual understanding of this down. So when x is 4, y is 1. So we can put a point there. And this is almost the same. We can maybe just say 1.5 or something. Not quite, I wouldn't say it's quite 2. But when x is 5, y is 1.5. So put a point, whoops. We'll put a point at 5, 1.5. Now, what's the point of this? Well, we want to recognize that, see, the derivative itself, you know, is a graph, is a function. And we can use this graph to, you know, model the behavior, how something is changing. And that's very useful in the real world, especially when we're dealing with, you know, motion of, you know, cars or airplanes or just, you know, all sorts of stuff. Because we want to understand, you know, obviously something speeding up, slowing down, in what direction, how fast. So now technically we would want to calculate every point between, or as many, to get an approximate, you know, idea of this. But just to give you an idea, now, like, let's actually do this. I mean, to make sure I don't confuse you more. Over here, this is like 0.5. The derivative actually goes back to 0. See how it gets flat there? So then, see, then at 0.5, see, I plot a point here. So it gets negative, 0, positive, and it's like 0 over here, negative, 0, positive. So that's what's going on with this graph. Negative spikes up all the way up to about so maybe say it's something like this. At 2. Whoops, that's not something. It actually gets really. So again, this is just a rough idea. This is not perfect, because, you know, to be perfect, we would have to go through many, many points. But this is what the idea is behind graphing the derivative of a function. We graph, you know, points, essentially x, and then we can say f prime of x. That's how these points would be, read. All right, now let's go through calculating the derivative using the limit process, and this is going to be an intense one, so be ready. These are going to, be at the exciting problems you're going to have to be ready for. So again, we're just going to, find the derivative using the limit process, which we did, earlier in the previous lesson. So limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Now, remember, we treat x, just as like that as the input, which, we have to be careful because sometimes students will get confused when we're dealing with this. And it's actually, let me write f prime. F prime is going to be equal to this. Now, remember, so this input is just the input here, which means this is going to be raised to the third power, and then it's going to be added to twice itself. So let me actually put this in double parentheses so it can stand out better. So this will be equal to the limit as delta x goes to 0. So everything inside here will be cubed. So we're going to have x plus delta x cubed plus 2 times x plus delta x. That'll be the first part. And then minus f of x, and then minus this whole thing. This x cubed plus 2x will replace that x there. So minus x cubed plus 2x. All over delta x. And now let's work some magic. So we go. This will be equal to the limit as delta x goes to 0. Now x plus delta x cubed, that's just x plus delta x plus times x plus delta x times x plus delta x. Remember, this 2 gets distributed to the x in delta x. So plus 2x plus 2 delta x. That whole thing is in that group. And we'll leave this, outside parentheses still. We don't, make a little mistake. These can be pretty tedious. All right. Now, multiplying this out. And then this is going to be, a test of, if your algebra skills are down. So, let's tutorial this first group out first. So we're going to have x squared plus 2x delta x plus delta x squared. And that'll be times x plus delta x. So plus 2x plus 2 delta x, all that in there. And then we can go ahead and then do minus the x cubed plus the 2x in parentheses still, all over delta x. All right, then multiplying this trinomial by this binomial. the limit as delta x goes to 0, we should get x cubed plus x squared delta x plus 2x squared delta x plus 2x delta x squared. Whoa. Plus x delta x squared. And then at delta x squared times delta x, that'll make it delta x cubed. So plus a delta x cubed in there. And then we're going to add this just so we're still here. So then add the 2x plus 2 delta x plus 2x plus 2 delta x. I think the brackets actually in. I should have been doing that. And let me put this in brackets so we can see it sounds out better. And then minus x cubed minus 2x all over delta x. Now this 2x and this negative 2x will cancel. And now here we got to make sure we're paying attention to common terms, because this is where you got to be focused. So this will be equal to the limit as delta x goes to 0. Okay, we're going to have an x cubed cancels out with a minus x cubed. And we have an x squared times the delta x. So x squared plus 2x squared. So then we're going to have 3x squared times delta x. All right, and then we have a 2x delta x squared plus an x delta x squared. So this and this will make a 3x delta x squared. So plus a 3x delta x squared. And then we'll just have delta x cubed here, plus a delta x cubed. Then plus a 2 delta x, plus a 2 delta x. Now, again, think of the delta x just like a variable. Think of it as like a y or a w. Then it won't be too confusing, because you remember, just like with like terms, you can't combine like terms unless the term is being raised to the same power. So here and here, it's just like a delta x and a delta x. You can combine those because you have an x squared and delta x, delta x. See here, it's like a delta x squared. So think of it as like a y squared. You can't combine it with that, but you can combine it with something that has an x and a delta x squared. So you think of it as like a variable. All right, and then just like a variable, you want to cancel out everything with the like terms. So everything has a delta x, you can see. So you can power it down, cancel out delta x here, delta x here, delta x here, delta x here, and delta x here. And then this ends up being equal to the limit as delta x goes to 0. Here, we're just going to have a 3x squared because that delta x went away. This will be 3 plus a 3x times the delta x. So we only powered it down, only one of them. And this will just be a delta x squared because it's like factoring out a y out of a y cube. And then this will just be plus 2. All over 1, because delta x divided by delta x becomes just 1. Now again, let's not forget what the whole point of, doing, this fun math was. It's because originally we can't divide by 0, which would happen if you plug 0 into for delta x in the original equation. But now there's no delta x in the denominator. So you're going to, okay to plug 0 into here and here. And so when you do, you're just going to get 3x squared. This just becomes a 0, plus a 0, plus a 0, plus a 2, all over 1. And then so we have that f prime of x, the derivative of f, is equal to 3x squared plus 2. I'm going to say over 1, but it's the same as that, 3x squared plus 2. So again, let's recognize that the derivative itself could be a function, or it's an equation. The equation of the derivative may not be simple, may not be always a straight line, or like a parabola. It could be something very strange we're going to see later on. So again, the derivative itself is a function because it could be some sort of polynomial, some unique behavior.